Good evening, everyone. Once again, welcome to the fifth day and to the second session of the fifth day. The second technical session of the fifth day for the sixth day ATAL sponsored online faculty development program on advancements in cloud and edge computing research and industry perspectives. The second session focuses on an advanced and application oriented topic, Edge IoT integration, which highlights how edge computing enhances IoT systems by improving latency, scalability, and real-time intelligence. It gives me great pleasure to introduce our second resource person for the day, Dr. Ragesh GK, Associate Dean, Industry Relations and Fundings at Indian Institute of Information Technology, Kottayam. Sir brings with him strong experience in academia, industry collaboration, and applied research. His session will provide valuable insights into practical strategies and real-world use cases of integrating IoT with edge computing. Sir, we are truly honored to have you with us. I kindly invite you to take over the session and share your expertise on edge IoT integration. Thank you, and over to you, sir.
Yes, so thank you for the kind introduction and hope I'm audible to everyone.
Yes, sir, you're audible, sir.
Okay. Since I'm not using any external, mic or something, I hope my voice is clear and evident, right?
Yes, sir, your voice is also clear.
Okay. Thank you. So good evening, everyone, and thank you for.
Welcome.
Yeah, good evening, Remini ma'am. Yeah. So thank you, Dr. Remini ma'am, and the other organizing team for inviting me to take a session as a part of this ATAL sponsored faculty development program on advancements in cloud and edge computing. Okay. And I'm happy to be associated with Adi Shankara again because many long years I spent there at Adi Shankara as assistant, associate, professor, and HOD of electronics department. And by 2021 only, I moved from Adi Shankara to IIIT Kottayam. So currently, my area of expertise is in Internet of Things, wireless communication, and I'm having two labs here, primarily focusing on drone technologies and also like idea to market kind of products development, etc. Okay, so coming to today's topic of discussion, Dr. Ajay has already given you a level of understanding on Internet of Things, how IoT is being clubbed with cloud computing and other underlying communication infrastructures. So nowadays, you know that this IoT or any other kind of technology, they are not actually working on a standalone manner. It's an amalgamation of different technologies for different use cases. So here today in this talk, I'm going to give you some insights, my experiences, and some research directions, especially on a topic like edge intelligence, which is again clubbed with IoT data, and it should have again a strong infrastructure to make it sense. So that's why I clubbed IoT with 6G, another cellular infrastructure technology, which has to be there to provide the actual meaning for edge intelligence. So I will be talking more on edge computing and all, but it's more about edge intelligence. So that's why the topic title is slightly modified into edge intelligence for IoT and 6G convergence. Here we'll be talking more about architectures, different optimization techniques and future research directions. So this is the overview of this particular session. So we know that, so we will be starting with the motivation for edge intelligence in large scale IoT as well as 6G communication systems. Next, I will be moving on to different associative or related technologies of edge intelligence, like edge computing, federated learning, and AI model optimization. And we will be also touching on the key challenges here, like the privacy, security, different resource constraints and scalability. And other parts like definition of, that will be second time. Like after motivation, we'll be going to the definition of edge intelligence, comparison studies and all. And I will also be talking about how this edge intelligence is connected with IoT and different cyber physical systems and 6G as the backbone communication network. And finally, we end up this presentation with, we have a discussion on research and roadmap and future directions for AI assisted or AI native 6G edge systems. Okay. So we all know that over the last decade, we have witnessed a lot of advancements or a lot of disruptions happening in the connected devices technology with the advancements happening in sensors as well as in other intelligent systems. And the IoT or the Internet of Things, which has moved far beyond you called a simple data collection kind of a technology, because it now is the backbone for many critical infrastructure. You know that IoT itself paved the way for different automations, especially our Industry 4.0 or many other autonomous systems, especially in autonomous vehicles and all. Lot rapid technology disruptions happen because of the advancements happening in the sensor industry, as well as the IoT ecosystem as a whole. And also we moved to smart healthcare because of this. We moved to intelligent transportation because of this. And also a lot of, as I was also hearing to what Ajay was mentioning in his PPT on last few slides about the environmental monitoring project that they are doing. So there also we can find a lot of, like involvement of this edge intelligence and IoT, etc. So similarly, in if you take a wireless communication, systems as a whole, they're also undergoing a lot of fundamental, transformations. So as we nowadays, the talk of the town itself is about the 5G, all right, and we are now doing a lot of research and activities, and the government has a lot of initiatives in the Bharat 6G vision and all. So nowadays, networks are no longer designed just to transfer data. As you might be knowing, like about the evolution of different communication networks. It started with the 1G and we are now marching towards 6G. And the earlier generations before 5G, we know that majority of them are just for transporting data from one point to another. But with the introduction of 5G and 6G, it is not about a mere cellular network. It is all about an underlying fabric, an underlying, intelligent fabric where you can have different levels of use cases meeting the demands of different users. Someone will be looking for reliability, someone will be looking for throughput, someone will be looking for data speed, yes, because that ultra reliable, low latency kind of communication, etc. So we move beyond this 5G and marching towards 6G networks, and these networks from 5G onwards or 5G and beyond networks are not designed for just transporting data from one point to another. Instead, they're actually evolving into more intelligent platforms capable of doing a lot of sensing. They can learn by itself, they can adapt to situations, they're context aware, and they could provide you some intelligent decision making, right? So that you can convert all those decisions into some business outcomes. So this convergence of massive, IoT deployments or the next generation kind of communication networks raises a critical question. What is the question? Like how we are going to process this large volume of data. We nowadays call it as a big data, right? How we are, because nowadays it's all about massive IoT, because the number of devices generating this data is enormous. Now itself, you can know that according to NASCO, every Indian, they're having at least 7 devices always connected to internet. They're all generating data. So how do we process all this data? How we are going to analyze this data, and what kind of action, or what kind of action that we can do on this data. But whenever we do some kind of process analyzing or acting upon such kind of enormous volumes of data, the question is, can we do it in a reliable basis? Can we do it on a secure basis? And can we do it in a real-time basis? Even if it is not real-time, there is no point of saying it's an autonomous system. Autonomous system, the word itself is embedded with real time. So if it is not doing any kind of real time activity in a reliable, secure fashion, then that technology or that product that we are building is no more. We cannot name it as an autonomous system, right? So traditional cloud-centric computing that already Ajay has mentioned, I hope he has mentioned some computing models and on. So these traditional cloud computing or cloud-centric computing models are increasingly insufficient to meet these kind of large volumes of data. Because majority of those cloud computing models that we are discussing are centralized in nature. Centralized processing are happening, right? Centralized processing, and you know that what are the benefits that this centralized processing will give you, and what are all the demerits, right? So one of those things, whenever we talk about this centralized processing, you need to think about, these kind of infrastructures will introduce things like latency. It will create, bandwidth kind of bottlenecks, because we are talking about wireless. I do understand that IoT is not always wireless, but 95% of the IoT communications are happening in wireless. So majority of these communications, since it is happening in wireless, they're all battery constrained. So we need to think about the bandwidth bottlenecks. We need to think about latency. We think about privacy concerns, because we are putting our private data on the cloud, and we are more bothered about whether, if it is healthcare data, if it's a financial data, people more care about those kinds of sensitive data if it is stored some away from the consumer side. So create some kind of bandwidth bottlenecks, creates a level of, it raises a level of privacy concerns, and also it limits scalability. So especially so all these kind of, what is that? These constraints are there for majority of the real time. These are the major concerns for many mission critical, applications, latency sensitive, mission critical applications. So this is where edge intelligence comes in, or edge intelligence emerges as a transformative paradigm. So it is a transformative thing. We are not actually replacing cloud computing with edge computing. We are now going for extended capabilities of cloud towards the edge side. So these edge sides will create a transformative paradigm. How? Because this edge intelligence moves the artificial intelligence and decision making very much closer to the data source side. So data source side, so that you will be more prepared for this kind of real-time perception. It will provide you, it will enable you with real-time perception. It will give you, you can learning happens there, and controlling happens at the network edge. So in parallel, when we take this notion of edge intelligence into 6G, we know that 6G introduces the capabilities. So why we are moving from 5G, 6G and on? Not only for data speed alone. It's not about how much data speed that you're getting out of the 6G. Even though the evolution of these cellular communication networks will give you better data rate, that is not the prime purpose. Okay, so the first capability, obviously, it's a ultra low latency. And second thing is the massive connectivity. These kind of devices, almost all devices, all gadgets now we are using are all connected. They're generating data by itself. And also, when we move from 5G to 6G, 6G have a better vision now, because we are going for integrating different terrestrial and non-terrestrial networks here. And so that when our notion of just connecting devices is become larger, that notion becomes wider, broader, then we need to have an external intelligence in place. So the AI native communications, AI is the core of 6G. You can look into that 6G architecture and see that AI is at the core. Without AI, there is no 6G. So so that's why it is AI native. Normally people will call 6G as AI native 6G. So it's AI native communication. They're non-integrated terrestrial and non-terrestrial communication networks all together will create the ideal foundation for a distributed data intelligence. So in today's talk, in this session, I will try to explore, how this edge intelligence acts as a key enabler for the convergence of IoT and 6G. And we will also examine some mainstream architectures, as I told you in this overview. And also we look into the emerging technologies in AI, as well as what are the challenges and open research directions. Okay. So let us begin with the fundamental question, like why this edge intelligence and why this discussion. So let us begin with this fundamental question of why do we need edge intelligence at all, right? So for many years we know that whenever we discuss about these cloud computing infrastructures, artificial intelligence or AI has been primarily cloud centric. It's not edge centric in its name way. It's a cloud centric one. So data generated by all these kinds of massive IoT devices, they're all transmitting these collected data into some centralized data center. And all these data is being processed there itself in the centralized data center. And the results or the feedback are sent back, right? That is what is called as, in whole together, we can call it a cyber physical system. So this model actually works reasonably well. Okay, cloud-centric AI model will be reasonably very well. It is good for delay-tolerant applications, not latency-sensitive applications. Delay-tolerant applications, that is fine, but it breaks down completely for latency critical applications, or when we take any kind of privacy sensitive use cases, then this cloud-centric AI intelligence will fail. Okay, two things. The one is it won't work for delay sensitive applications, for latency critical applications, and for privacy sensitive use cases, because data sovereignty is not maintained in cloud centric networks. Okay, so that's why you can take different kinds of healthcare setups, even though in India also witnessed many such kind of agreements with US about transferring our data to US cloud centers, and people in Kerala, they protested a lot for that because about data privacy. So consider that you can take, so whenever we are bothering about this latency sensitive or privacy sensitive use cases, immediately we have many kind of things coming to our mind. The first thing will be about we were discussing about autonomous cars nowadays, autonomous vehicles. So consider applications such as autonomous driving or remote healthcare monitoring, or as I said about industry 4.0 or smart factories, or about any other kind of public safety systems. In all these kinds of use cases, that even a very few milliseconds of delay, can lead to incorrect kind of decisions, or it will produce some kind of unsafe outcomes. So sending data to a distant cloud and waiting for a response from the cloud simply is not acceptable in these kinds of latency sensitive, privacy preserving kind of use cases, right? We cannot wait, because that whenever we are generating a data from one point, it will take some, for example, time T1 for generating of data, time T2 for sending this data from the cloud, from the data originating side to the cloud. Then processing will take another time, say T3, and sending a feedback back to back to the originating side again T4. So it will be hardly taking some T1 plus T2 plus T3 plus T4 is the total time for processing, getting the data and processing it and getting a feedback and generating an outcome. So these kind of delay is not tolerable in privacy sensitive applications as or latency sensitive applications like autonomous cars, autonomous vehicles, autonomous driving, smart healthcare, smart factories, etc. So in all these cases, that we need split fraction second decisions. Even a few milliseconds of delay can lead to some incorrect, unsafe kind of, outputs or outcomes will be generated out of that. So sending data to a distant cloud and waiting for response is not at all acceptable in these kind of use cases. But at the same time, that the scale of IoT, the scale of IoT deployments is also, going in an exploratory manner, right? It is exploding like anything. So billions of sensors are available now. You know that because majority of the institutions now they're having IoT labs. They're all working on different use cases. Even Adishankar is also working on an IoT kind of a big project from IT about environmental monitoring and about near the Karadi area and all Periyar River basins and all. So billions of sensors and devices are like the same scenario, like continuously generating massive amounts of data. And just backhauling of all these kind of raw data, uh, to the cloud is not only inefficient, but at the same time it also places an enormous burden. It isn't like a cloud burden and all the kind of stuff, all the kind of data stuff we are pushing the data to the cloud. So we are actually overburdening the cloud like anything, and it is overburdening the bandwidth and infrastructure. But now with the emergence of these kind of intelligent cellular communication technologies like 5G, 6G and all, the expectations are more even, very, very stringent. So that's why every cellular, evolution takes some 10 years. You know that 2020 5G came. Now we are expecting 6G in 2030 because 10 years of time is needed for such kind of an evolution. And the same thing happens for 4G, 3G, 2G and all. So with the emergence of 6G, we are having as a customer, as a provider and all, we are having more expectations on such kind of technologies. So 6G applications require more. It is more for real-time autonomous applications where ultra low extreme latency is expected, extreme high reliability is expected, and intelligence must operate at the same time scale as as with respect to that of the physical processes. So fortunately, we have these kind of edge devices today, and they are no longer, it is no longer like a simple, say like a sensing unit. They are equipped with significant, computational capabilities, including, about the AI accelerators, and they could make some, local inferences, where there is inferences from the data generation side itself without moving away from the data generation side. So that, it makes those decisions very local so that finally the users, the data consumers or data owners, they have that privacy thing, they have that trust thing comes in when they are storing everything on the edge side. So privacy regulations and trust considerations, etc., is, it is being preserved with the help of this edge computing. So all these factors together, all these kinds of factors, what we have discussed together, make this edge intelligence not just an optimization of the existing systems, but this is the need of the hour, need of that architectural shift from the older 4G or the mere kind of sensing equipments to more intelligent, more futuristic kind of IoT integrated 6G networks. So this naturally leads to, the next question that is being answered in the next slide. That is what exactly do we need, or what is exactly this edge intelligence? So now we understand. So that why part we have finished in the first slide, why part. So let us clearly define what exactly this edge intelligence means. So this edge intelligence, that it refers to the uh, the deployment of your artificial intelligence algorithms directly at the network edge. That is, when I am saying at the network edge, I don't mean that it is on the device itself. It could be near the device also. Okay, on the device or near the device where data is generated. But we know that from the traditional, data center architectures and all, we know that everything is being forwarded to cloud for processing, but edge intelligence data is actually processed locally, and decisions are actually made very much closer to the data generation side. So this kind of, a shift significantly reduces, as I told earlier, like it significantly reduces the latency, because data no longer needs to travel back and forth many times. So distant travel, those things can be avoided. And also it also, significantly reduces latency, also that bandwidth consumption and other kinds of, resource preservations, etc. Because everything that model up, the majority of those data processing will be happening at the edge itself, and we are just forwarding, some kind of model updates, kind of thing, some relevant, like, many only relevant information, so some kind of relevant insights or some model updates are only transmitted instead of these raw data streams to the cloud. Okay, so another key advantage I told you about the privacy. So sensitive data, because majority of the edge computing infrastructures, if you see in literature as well as in companies like Siemens or Bosch and all, you can see that all those infrastructures are mainly into these kind of, patient related or person related kind of informations, because these are all, sensitive data such as the health information or location information or personal informations or some, some parameters. So such kind of local parameters, etc., will be like, will be exposed to something like it will be opening the back doors for attackers to do some kind of malicious activities. So that's why everything is being preserved on the edge side. Okay, and majority, so most importantly, that nowadays we are talking about the context aware things, right? Context aware. So edge intelligence actually enables the kind of, the real time and context aware kind of intelligent services. So decisions can be made immediately, like, whenever we are telling about these autonomous cars and all, you need to apply the automatic braking, right? Whenever a pedestrian is crossing the road, the dashboard inside that car has to take decision by itself on a split fraction second without forwarding the data to the cloud and wait for some commands from the cloud. It is not permissible at all in such situations. So decisions has to be made based on local conditions, which is very much critical for applications such as these autonomous systems or any kind of, whether we call it a smart infrastructure. Okay, so I can tell you in simple terms that edge intelligence now brings the brain of those, brain of system very much closer to this kind of, data generation side or consumers or the data owner side. So here in this figure, you can see that on the top, it is all about the evolution from the cloud computing, and finally it reaches the edge intelligence, right? It starts from cloud computing to edge computing and then finally reaches the edge intelligence. So at the top, you can see the Netflix, the what is that, AWS, the Google Cloud and YouTube and all those things. So we have many centralized cloud platforms available. So some examples have been highlighted there, like AWS, Azure, Google Cloud, etc. And these offer high computational power. We know that how Netflix uses anything, not only Netflix. Ajay was telling about this kind of cloud infrastructures like Microsoft Azure or Google Cloud, etc. So these offer, even though these offer like high computational power, but they're all very much far away from the end users, right? So this also resulting in what we called as latency and bandwidth overhead. So here in the middle layer, you can see the middle layer where represents the edge computing, where computation is pushed closer to the users, through some base stations and the edge nodes, right? So this reduces latency, but you should understand that even though it reduces latency, but it mainly focusing on data processing and rather than intelligence. So that's why we have two branches, edge computing and edge intelligence. Edge computing is more into like how processing has to be done. There is nothing, the edge computing devices has nothing to do with intelligence. So that's why this, even though it reduces latency, but it mainly focusing on data processing rather than running an intelligence thing on the edge side. So at the bottom, you can see different kinds of end devices, such as different smartphones. You can see their sensors are there, vehicles are there, that are continuously generating real-time data. And edge intelligence goes actually a step further by embedding this AI-driven decision making at the edge, enabling real-time, context-aware, privacy-preserving intelligence services. Okay. So moving on, so we have this evolution from cloud computing to edge intelligence. Right, so you can see here the low latency. So it started from 1990, where we have the content delivery networks came. Then in early 2000, we moved to the peer-to-peer kind of communication networks. And the early 2010, we moved into our micro data centers were introduced, and 2020 we talked about, and many of the applications have been moved to the edge computing. So to make you understand edge intelligence more, more in depth. So this will help to look at how computing paradigms have evolved over time from 1990 to 2020. So we began with some traditional cloud computing, where data generated by end devices is transmitted to centralized data centers for processing and decision making. And this model, that this kind of a model offers a lot of scalability, right? Scalability and many powerful computational features came. But ultimately, we can see that when we move towards this kind of, automation kind of thing, then it introduces latency issues, bandwidth overhead issues, and privacy concerns, right? So as I told you, like when we are saying that as we move from, as we, one second. Sorry, mouse and okay. So as applications, as applications became more interactive, that's what that we more interactive, and there is a rapid, the increasing of data volumes because of this massive devices, edge computing emerged. Okay, again, emphasizing the importance of edge computing, migrating from the early content delivery services, and now we have edge intelligence in place. That's it. So here again, there is a because many of the times we interchangeably use edge intelligence with edge computing and sometimes with cloud computing as well. So at this point, it is having some issues with the mouse. Second. Okay, so at this point, it is important to clearly distinguish how this edge intelligence from the traditional cloud computing and edge computing, as these terms, as I said, like as we are using these terms often interchangeably. So this figure you can see here, this figure compares that on device intelligence with edge intelligence and cloud intelligence across different key performance dimensions like privacy, latency, diversity, scalability, on-device cost, and reliability. So on-device intelligence, what is that? On-device intelligence means, that it offers some strong privacy and low latency. But at the same time, even though it provides strong privacy and low latency, it is limited in scalability, right? Because model diversity is missing here or limited in scalability because of the resource constraints. Because it is all about on-device intelligence. So there will be a limitations on scalability side as well as on model diversity side due to the resource constraints. So when we talk about the cloud intelligence, so cloud intelligence, it provides high scalability, and there is a room for, there is a model diversity available, but again, it suffers from, say, like high reliability and higher communication cost and weaker privacy. Okay, so when we move from cloud intelligence to edge intelligence, it lies between these two extremes. That is achieving. So there is a kind of I can say that it's a balanced kind of trade-off. So edge intelligence has to lie between these two extremes of on-device intelligence and cloud intelligence so that it could achieve a balanced, balanced trade-off. That is, when I'm saying balanced trade-off, it significantly reduces latency and it improves the privacy compared to the cloud while still offering a better scalability and reliability. Okay, so overall, the entire figure highlights or tells us, the importance of edge intelligence or edge intelligence, how this edge intelligence is more practical compared to the cloud and on-device, intelligence, and how it provides a balanced solution. How this edge intelligence provides a balanced solution for real-time, scalable, and privacy-aware intelligent systems. Okay. So now we move to this, the next, we talk about what are the key enabling technologies of edge intelligence. So till now, we have seen that why edge intelligence provides the best balanced kind of solution. Now let us have a look at, what are the key enablers for that. So the first and foremost or the most fundamental component here is edge computing infrastructure itself. Without edge computing infrastructure, we cannot think about the edge intelligence, right? So when I'm saying, when we are describing this edge computing infrastructure, so these are all the different components or these are the backbones of any edge infrastructure. That is, it consists of different edge servers, it consists of different edge gateways, it consists of different base stations, and also different micro the data centers, which are actually all these things, all the edge servers, gateways, base stations, micro data centers, etc. are deployed where? In edge computing, they're all edge infrastructure, they're all deployed very much close to the user. And these provide the computational foundation for running different kinds of AI models outside of the cloud. So that's why I told you in the beginning, we are actually extending the capabilities of cloud. It's an elastic thing, right? We are actually extending or bringing or pushing the capabilities of cloud towards the edge side. So that's why on top of this infrastructure, you can see that many artificial intelligence and machine learning algorithms will be deployed. I'm not saying that even heavy AI or ML models can run on edge devices, but there are limitations. That's why, but even if depending upon the user scenarios, some of those models and applications can still run on edge side. So these models, these edge-centric models perform tasks such as, the first thing is perception. And second thing is prediction. And the third thing is after prediction, it's all about decision making, right? Decision making all together, all the operations, perception, prediction, and decision making, everything happen at the edge, enabling these real-time responses. And you can say that nowadays people, even my research scholars, are also working on different federated learning algorithms. So federated learning, we know that federated learning has a lot of scope in healthcare data, right? Healthcare data sharing. So whenever, many hospitals are, working on a single project, they do not want to share those private sensitive data. So these kind of federated learning actually plays a crucial role in such kind of collaborative model training across different distributed edge devices. Why? Because in federated learning, we are not actually sharing the raw data itself. So this is very much particularly important for such kind of privacy sensitive applications. So IoT devices here act as just like a data sources, continuously generating these kind of real world, information. You can take the example of a W band, a wireless body sensor network and all. From there, a lot of healthcare data is being generated. So, these sensors, even though it is not about sensors, the body sensors alone, you can take the example of surveillance cameras as well. Nowadays, in Indian roads, you can find a lot of surveillance cameras, and they're taking some edge intelligence by understanding, whether the vehicle is moving at a large higher speed or not, speed limiters and all those things. So cameras, they're also data generators, and also different kinds of these generators will provide you some actions with the help of actuators. So without reliable sensing or edge intelligence, edge intelligence or edge computing infrastructure will fail. So we should have a reliable sensing. Then only edge intelligence can function in a reliable manner. So high speed and low latency communication technologies like our 5G or 6G kind of a very good supporting communication infrastructure have to connect these kind of devices, edge nodes, as well as with the cloud. So these networks ensures that, intelligence can be distributed at the same time it can be coordinated efficiently. Okay, so in these kind of key enabling technologies like 5G, 6G, federated learnings, or any kind of actuators, sensors, etc., all these, so we can say we can see that it is a tight integration of all the different levels of technologies that makes this edge intelligence more, more practical, possible, scalable, and effective, right? So that's why nowadays we all say, like, whenever there's an IoT, normally people will say like it's a cloud assisted IoT. It's not just IoT, it's a cloud assisted IoT, or people will say that AI IoT, that is artificial intelligence enabled IoT, right? So that's why two different technologies are now tightly integrated so that we can have a better ecosystem, right? So now you can see this is one of the interesting papers. Sorry that I didn't mention that paper name over here, but I can share you through your organizers. This is a paper, latest research paper published in IEEE Communication Surveys and Tutorials, where the entire paper is all about how we can integrate edge with 6G and IoT. So from that paper only, I grabbed this particular, a comparison table among different edge intelligence, edge computing, and cloud computing. So this comparison, you can see that different features have been listed over there, starting with computation, location, latency, processing, resource capability, security and privacy, etc. So this comparison is particularly important from a research perspective, because as it highlights how the focus shift across cloud computing, edge computing, and edge intelligence. So cloud computing, that it reaches traditionally emphasizing the scalability, the scalable architectures and all, high performance computing, resource management, and handling different levels of complex, computation incentive, compute incentive kind of workloads, etc., in a centralized environment. So edge computing research moves that focus towards a decentralized or a distributed kind of environment where it is giving a lot of importance for a low latency kind of architectures, task offloading, and efficient coordination between different edge nodes as well as with the cloud. So this particular comparison table gives you more understanding about how this edge intelligence represents a strong research shift towards an embedding kind of AI and machine learning in a resource constrained environment. Why I'm saying resource constrained? Because you know that you can take the case of nowadays we are talking more about drones or flying IoTs. So flying IoTs, you know that these drones are also like edge devices, right? Majority of now the drones are autonomous in nature. Now we are actually developing a drone, which is a indigenous kind of flight controller without GPS. Without GPS, a GPS denied environment, we are leveraging technologies like SLAM. We are leveraging technology sensors like that lidar, etc., for making so that these drones or the unmanned aerial vehicles have a smooth operations in an indoor environment first. Then we will be extending that capability to the external environment. For the time being, it is been research been happening in the indoor environments. So there also we are actually doing we are giving intelligence to the drone to take some decisions by itself. Okay, so there are different use cases for that. So this kind of a comparison table actually tells you about how this edge intelligence represents a strong candidate in supporting such kind of use cases, with some key challenges also. There are some key challenges also, including the resource constraint, because prawns and all, you know that we have some limited memory capacity, or even if we are using boards like Raspberry Pi or Jetson Nano or Jetson Orin kind of boards, etc., it has many limitations, right? So there are different resource constraint limitations available, but again, we are going with such kind of things for autonomous decision making. Yeah, any questions in between? I heard some noise in between, so that's fine. Any question?
Sir, I thought of asking at the end, shall I?
Okay, sure. You can, please. Yeah, go ahead. If you have any question, no problem. Okay, no problem. So if you're asking at the end, can I continue? Shall I continue? Shall I continue?
Yes, yes, sir. Yes, sir.
Okay,
But
okay.
Sir, one communication in your chat window. Could you?
Actually, I'm just seeing my what is that communication?
Okay. Then we can take the questions at the end. That would be
You
fine.
can ask me. You can just
No,
read it
I
for
have
me. I'll
seen one
answer it.
question I have a question that I'll ask at the end, but there's a
Okay.
question in the chat window that we can take it at the end. That's fine, sir.
Okay. Yeah. So here the current research. If you ask me about the current research happening in the edge intelligence, you know that nowadays, since we are actually extending the capabilities of cloud towards the edge, the researchers are now working on lightweight models. Even in my case, I have a funded project from C3 iHub of IIT Kanpur, where we are doing a project on secure UAV, multi-layer secure UAV. We are actually providing security at the physical, data link, and application layers. So in physical layer approach, what we are doing is we are trying to defend different kinds of jamming attacks. Okay, and for that, different use cases that we are doing, like drone to drone communication, drone to ground station communication, as well as a spam communication. So how it can defend these kinds of attacks. And we are actually working on different secure NOMA, that is non-orthogonal multiple access kind of technologies, especially in the physical layer, to defend such kind of attacks. Again, AI has a huge role to play there. But again, this is one of those works that we are currently doing. For that, we need some kind of lightweight cryptographic models to work on the physical layer. Because we are not actually we are not running those models in a downstation server. We have to run those models in the drone itself on some, as I said earlier about the kind of boards that we're using, the Jetson Nano or Jetson Orin or kind of similar kind of boards. So there we need to explore different kinds of lightweight models. We need to we need to incorporate machine learning, like federated learning algorithms over there. We need to have some kind of online learning. Online learning should be there. And majority of the time, since this is drones and they are using for different kinds of use cases like disaster management or such kind of mission critical applications where self adaptation is needed. So we need to work on that kind of self-adaptive algorithms, especially in the edge side, that allow systems to respond intelligently in real time without relying on the cloud connectivity. So overall, this kind of evolution, one second, I'm sorry. I'm having some issues with the mouse. Okay, so here, yeah. So overall, these kinds of evolution like edge intelligence, cloud computing, then to edge computing, and then into edge intelligence. This evolution actually reflects a kind of transition in research from improving. So nowadays, people are more into designing context-aware systems rather than working on the computational power aspects. Right. Before, when people were doing, I know that because during my PhD days in 2015, that time people were more working on the cloud computing, computational power adaptation kind of thing. But now the research has been shifted from the computational power to designing more intelligent, more autonomous, and more context-aware kind of systems operating at the network edge. Okay. I think I'm going a little bit slow now. It's 8:21, spending more time on certain slides. Sorry for that. So edge intelligence and technology stack in IoT 6G. So up to this point, we have understood, we have built a conceptual understanding about edge intelligence. So now this is, it is time to move on to the core technical, framework like edge intelligence, saying like it is not at all a single technology, but it's a tightly integrated network. As I said earlier, it is a tightly integrated stack built on the top of IoT and 6G systems. So at the foundation of the stack, you know that there is edge computing are there, which provides the execution platform for running different kinds of AI models close to the data sources. But on the top of that, you can see, we can see that federated learning has a huge role to play there. Instead of collecting these raw data, centrally, models are trained collaboratively. So like my own student, Lekha, she's a PhD scholar here. She's working on federated learning on healthcare data in like incentive analysis, incentive federated learning mechanisms, and she's doing an internship as well in Aravind Eye Care Hospital in Chennai, where they're working on these kinds of patient-centric data, especially on eye diseases. So they are collaborating with the different Norway-based healthcare sectors, and for that they are actually building a federated learning architecture, a framework there that plays a critical role. So here also, why federated learning? Because instead of collecting all these data, processing data centrally, models are trained collaboratively across distributed IoT and edge devices that directly, addresses different privacy and different other kinds of policy-based or regulatory-based kind of constraints. Okay, so here, so that is why. So here you can see that majority of these models are heterogeneous in nature. Because why heterogeneous? We have different varieties of IoT devices from different manufacturers and all. They're all ranging from different capabilities, like on the resource management side or resource constraint side. So we have different heterogeneous IoT devices ranging from resource constraint sensors to different powerful edge servers. So this is why we should have an underlying strong communication infrastructure. That's why I'm just trying to club this edge computing with 6G. So 6G becomes a key enabler here. So unlike the previous generations, even 5G also, 6G is designed to support AI native communication. So if you know about 5G technology, you know that AI is not at all not have a prime role in 5G technology, right? AI is a kind of a supplementary service in 5G technology, but For 6G, it is a key player. So that's why it is a AI native communication in 6G. So which provides many ultra low latency, and there is a tight integration between this communication and computation in 6G setup. So overall, this kind of this technology stack reflects a kind of shift from isolated end systems to moreover a cross-layer kind of design. You can see that a cross-layer kind of design where intelligence is having a prominent role along with the communication and computation. Altogether, they are jointly optimized, right? Then moving from so edge computing as the execution platform for edge intelligence. Now, okay. So now let us focus on the first concrete kind of building block of edge intelligence, that is edge computing itself. So in 2025, so I have captured this slide from NASCOM website, where they have a discussion. There is a white paper available on the edge computing infrastructures, and from there I could understand that these are the best edge computing platforms of 2025. So edge computing provides the sorry that I'm just having some issues with my mouse. That's why going and coming and back. So edge computing actually provides the the physical as well as the virtual execution platform on which we are actually operating the edge intelligence. So you may be knowing it, like what this edge computing consists of, this infrastructure consists of. We have a lot of edge servers there. We have the gateways, we have the base stations, we have the different kinds of, if you're taking autonomous intelligent transportation systems, all these roadside units, your traffic controller units, etc., becomes intelligent. So roadside units also a part of this edge computing infrastructure in an intelligent transportation use case. So different kinds of micro data centers will also be available, which are deployed close to where the data is being generated. So instead of forwarding the, as I told, the raw data into the cloud and all, these edge nodes execute the AI inference locally itself, and this allows decisions to be made within milliseconds. So these are the best edge computing platforms available, like Azure IoT Edge, even for my research as well. Since my research was concentrated mainly on the building secure and cryptographically enforced kind of patient health record systems, PHR, or electronic medical record systems, where we are getting all this data from different wireless body sensor networks, and all this data will be forwarding to a cloud infrastructure. That time we were not concentrating on the edge side, but we were more into the cloud side in 2015, I'm saying. So then edge, so there also sorry. So during that time, I also used my PHR system as IoT, this Microsoft Azure, because majority of the PhD works during that time, we were using this Microsoft Azure as the cloud platform. So in 2025 also, it is, I'm happy to see that since after this, many new IoT means cloud computing paradigms evolved, even though Microsoft Azure IoT also itself listed as one of the best edge computing platforms. Okay, then we have the Clear Blade, where software for industry IoT applications is there, and Eclipse, IBM backed the kind of platform for enterprise scale edge applications. So edge intelligence system architecture. So here you can see that presents a high level system architecture for the edge intelligence, often referred to as the IoT edge and cloud continuum. So at the lower level, you can see that this is the device level or the device layer, where we have different sensors and controllers. So we have IoT and devices such as sensors, cameras, vehicles, wearables, etc. there at this device layer. And these devices continuously generate real-time and highly heterogeneous data, because we know that the data generated by autonomous vehicles is entirely different from a wearable health-based device, right? So these devices continuously generate real-time and highly heterogeneous data from the physical world. Directly above them are the, the edge layer, where you can see the different edge nodes, gateways, base stations, as I said, like micro data centers, etc. And these edge devices host AI models that could perform different local inferences and real-time data decision making. So by processing this data at the edge, the system significantly reduces the latency and all, and it is actually, if there is an urgent, if it is not, it cannot be processed at the edge layer, those selected data will be forwarded only to the cloud layer in order to reduce the burden, reduce the processing burden, and reduce the bandwidth burdening at the cloud layer. So the cloud layer actually still, it plays an important role here. It provides a large scale storage and global model training normally happens at the cloud layer, but but it again have a good coordination with the edge nodes. You can see that when we there is some more there is in between layer as well, between the cloud and edge. We normally call it as a fog layer. Fog layer is again a layer which is again a far away from the cloud, and it has not been reached at the edge, but it is a fog. So like it is like a cloud fog and that edge computing, right? So rather than replacing everything on the cloud, here the edge intelligence enables a kind of a collaborative architecture where intelligence is distributed across different heterogeneous devices, edge nodes, as well as with the cloud. Okay. Okay, so yeah, at this point of time, do I want to answer something? Madam, if you could please read out that question, I could answer it and I can move forward.
Okay. Intelligent edge, edge intelligence, and edge computing sounds almost the same. What could be the difference between these?
That's what. Edge computing means we are actually extending the capabilities of cloud and doing those computations at the edge itself. But there is no meaning that we are running some AI algorithms there. But now what we are doing is we are actually running all these kind of AI based algorithms at the network edge. Okay, so rather than computing, so previously, formerly, our major interest was extending the computing facilities from cloud to edge rather than putting AI at the edge. Now, after this introduction of 6G and all, which AI is at the core of 6G, we have to do a lot of intelligence to be run at the edge rather than sending data again to the cloud and doing some AI based things at the edge and getting it back. So those things won't work in many real world applications, use cases. So that's why AI is now happening. These intelligent algorithms are running at the edge side itself, not only computations, but the intelligence also, decision making also happening at the edge itself, rather than depending on the cloud. So that's the difference. So edge computing means we have the edge node servers, etc. We are doing the computing, all those things there, but these intelligence, the decision making is not at all a part of edge computing. So more emphasis of intelligence is that context aware or self aware kind of networks are now building, as I told the case of drone to drone communication, whether drone has to flip, whether drone want to move forward or backward, whether it has to avoid some kind of obstacles. All this kind of intelligence has to happen at the edge side itself, rather than extending, putting those things at the ground control station. So that's why I told you edge computing is different. This is all about intelligence happening at the network edge. Okay. Whether I have answered the question or not, or do you have a different question? You can unmute your mic and ask, no problem.
Okay. It is being asked by Miss Annie Harish. No, I didn't. Okay.
Ani Harish, are you satisfied with my answer or not? Okay, so I think any answer in the chat window, ma'am? No.
No, sir. No.
Okay. Okay, then moving on. So we now move on to the role of AI ML in these edge environments. So you know that traditionally, so this could be an answer to what uh, the attendee just asked. So traditionally, we know that these AI models were designed for centralized cloud environments with abundant, we know that a lot of computational facilities and storage facilities available. But edge environments are fundamentally different. They are all resource constrained, right? All edge devices are resource constrained. They're highly heterogeneous because all the examples like smart environments, your intelligent transportation, healthcare, factories, agriculture. So all these things, they are heterogeneous. The sensors, the equipments, the algorithms, etc., heterogeneous and operate under different dynamic network conditions. So despite of all these kind of network or the kind of device or environmental constraints, modern AI, especially, like the large scale models has demonstrated that, there are having these large scale models are having remarkable kind of capabilities in pattern recognition, in learning and decision making. In this, I can quote you one example. Recently, we developed an electronic nose for Ayurvedic aroma analysis. And this was a funded project from IIT Indore under Drishti Foundation. You know that all these IITs, they are having different cyber physical system setups. They are giving fund for government, even for non-government, even UG scholars, PhD scholars, even for faculties and all for doing their, research-oriented work. So likewise, we actually participated with Ayurvedic, manufacturers in Kerala. And from them, we understood that there is no benchmark system available with them to evaluate the quality of the Ayurvedic products that they're producing. So even the Ministry of Ayush don't have a benchmark system to check the quality of the Ayurvedic products. We Keralites usually have a belief that all Ayurvedic products are generally okay and they are actually safe for consumption, even though we didn't, even many of the times we do not look into the expiry date of all those things. So we developed a kind of, the what is that? An electronic nose, an artificial nose for evaluating the quality of different Ayurvedic compositions. So you may be knowing that many of the Ayurvedic compositions will produce, okay, for produce a lot of gas. Means it emits gas. It emits gas, and these gases can be, sensed using different kinds of sensors like metal oxide, mock sensors. Okay, so we built actually 16 array of sensors, and these sensors can capture all these gas emitting. I'm not saying all Ayurvedic herbs and plants and compositions can emit gas, but majority of them can emit gas. Okay, because the majority of those compositions will consist of herbal things like tulsi, ginger, and all those things, and majority of them emit gases. And metal oxide, most sensors can detect all these gases and can produce some kind of patterns. So we convert all these kinds of sensitive data into different kinds of patterns, but it was just like supervised learning kind of algorithm we have used there. Okay, and because we already labeled it mainly, which are all the good products and which are the bad products and all. And from that, we have a reference model, and we compare different products patterns with the reference model. And we arrived at a conclusion after some 10,000, 20,000 kind of sampling we done. And we finally arrived, we in between AIMS Delhi as well came in between to check the product quality. It means the prototype that we developed, the quality and all. We went to AIMS Delhi for the product exhibition, and we got some good feedback from the doctors and even from the director of AIMS Delhi. So they actually, so initial case, we got an accuracy of some 72 to 75%, but when we submitted, we got a TRL level 7 product, and it's already patented. Technology readiness level 7. It is market ready, and it is being used by Vaidyanathan Foundation. which is in Ulur in Thrissur. They are actually in a pilot study now. So why I am mentioning all this means this device is not actually connected to any kind of cloud computing to have an analysis and all. But we know that these small devices, even the device that we developed, is only can handle only 1 to 2 kind of mini, like minimum sized bottles of these compositions. So it can be extended to some conveyor belt kind of thing, but for the time being, it's a prototype. So not prototype, it's like consumer ready, but it can handle up to 2 different kinds of medium sized bottles. It is giving under ambient temperature. So it provides kind of patterns and all, and it is never contacting with any cloud, and there is no Wi-Fi enabled kind of thing. It's everything happens at the constrained device itself. So that's why I told you these kinds of modern AI models, even though they are remarkable in pattern recognition, learning, and decision making. So if we are deploying such kind of if we are deploying such kind of large scale models in these kind of uh, uh, modern enterprise kind of environments, so it provides so sometimes I'm not saying the case of this electronic nose or artificial nose, but sometimes when we are extending such kind of models to the edge, sometimes we feel like it is impractical because of the latency or memory or some other kind of energy. Energy is also important here, right? Because these are all energy constrained devices, so energy limitations are there. So these limitations actually necessitate, it actually tells us all the researchers who are working in such environments to go for new approaches where you can have some model downsizing, that large scale model to a more convenient kind of simple model downsizing. So we have different kinds of architectures now available. One of those architectures is NAS. Have you heard about it? NAS? NAS means this neural architectural search, which plays a critical role by automatically, discovering the model architectures that balances performances with computational cost. So through NAS also, like intelligence can be systematically adapted to different kinds of edge environments, transcending traditional kind of manual based designs to more efficient based edge deployments. Okay. Then we are moving then to the adaptive, federated, and autonomous edge intelligence. So adaptive intelligence, it is what to say. Adaptive intelligence, it adjusts complexity at these runtime. Whenever we are going in a runtime environment, this adaptive kind of intelligence always layers some adjust the complexity. So knowledge distillation also here, the knowledge distillation also enables a kind of lightweight yet capable kind of models. So federated edge intelligence supports such kind of, I told you about whenever we are going for a collaborative model, privacy preserving can be, so that's why federated learning is most preferred for such kind of, sensitive kind of data sharing networks. Okay. So I'm just rushing and moving because now it's 8:45. So then the next model is the AI model deployment across heterogeneous IoT devices. So once these kind of models are trained, we often use different machine learning algorithms, especially these kind of federated learning algorithms. This is the next major challenge, because in deploying such kind of federated learning in different edge environments along with IoT. So we know that unlike these kind of cloud data centers, IoT and edge systems are highly heterogeneous. Devices come with different levels of capacity. For example, the processing power will be different. They're having different memory capacity. They're having different energy availability, and that different manufacturers, for example, Siemens and Bosch, For example, they're all working on healthcare sector. So nowadays we are actually working on something called as a digital twin for healthcare, especially along with the Amala Hospital in Thrissur, as well as with Malabar Cancer Center in Kannur. So they are along with other parties like CDAC, Trivandrum and all. So here there also you can see that these manufacturers, it's Siemens as well as Bosch and all, they have their own different hardware in architectures. They're all different in processing power, memory capacity, energy availability, etc. So so what I'm trying to say is a simple kind of, if you take a simple kind of sensor node itself may have only very few megabytes of memory, while the base station may have that kind of a GPU kind of acceleration. So deploying the same AI model across all these kinds of devices is not possible. So this kind of heterogeneity actually have a huge impact on this edge intelligence, because AI models must be carefully adapted to the capabilities of each device. So that's why I told you in the introductory slides that we cannot do all the kind of AI models in a particular use case. Depending upon the use case, we are actually extending the capabilities of cloud so that we don't want to overburden the cloud with mere raw data, right? So this heterogeneity actually indirectly impacts the edge intelligence, and that's why we need to look forward to have different AI models that could be adapted to the depending upon the capabilities of different edge devices. So when we go for these kind of large, the complex models and all, that could be working very well in the cloud computing setup, but we need to have a lighter models of such kind of AI algorithms to run at the edge. So without having a proper adaptation, this model deployment can lead to this kind of excessive kind of latency or energy drain. So that's why we are having energy aware kind of algorithms has to be there, or even it can bring some unforeseen situations like system failures. So this kind of, therefore, I'm trying to say that, effective edge intelligence systems must consider these kinds of device heterogeneity as a first class design constraint. And if you people are looking of a secure system design, security is also a part of this edge, because majority of these kinds of sensor devices are lacking inbuilt security. We know that these sensor devices are very much, for example, I'm saying these sensor devices are very cheap and they come with very minimal level of security, sometimes no security at all. And they come with some weak passwords as well. So that's why now majority of cybersecurity researchers, if they're interested in the hardware side, they're working on certain lightweight cryptographic models along with, whether the system by design, secure system by design to defend attacks like timing attacks, power attacks, as well as the other kind of side channel attacks. So effective edge intelligence systems must consider such kind of device heterogeneity as a first class, as an important design aspect. And this is one of the constraints, and nowadays, very few researchers are working on that secure system by design. So this challenge, this can be considered as one of the challenges that motivates many of the researchers to work on different optimization techniques that we will be discussing in the coming slides. So here, so to make these kind of edge intelligence optimization more practical, we cannot rely on different isolated optimizations, right? As I told you, we cannot rely on isolated optimizations. Then what we have to do? Instead, this kind of edge intelligence requires more systematic, more multidimensional kind of optimization approach. What do you mean by multidimensional approach here? So here, the first dimension should be the task offloading. The first dimension should be the task offloading, where each intelligent task must decide whether it should run on the device at the edge or it has to be forwarded to the cloud. So this decision depends on factors such as latency constraints, factors such as computational load, as well as the availability of the resources which is there with the edge side. And the second dimension is the network coordination. What is network coordination? Here, we know that different edge intelligence systems are there. They are operating under different varying network conditions. So we have to look into the efficient usage of bandwidth, latency aware kind of routing, latency aware kind of scheduling mechanisms and coordination mechanisms, and when different edge nodes are essential to maintain a real-time maintenance. Real-time performance. So the third important dimension is the AI algorithm itself. So we have to work on different AI algorithm optimization where the models must be adapted to different edge environments through techniques like simplification techniques, restructuring kind of techniques, or sometimes we go for some partial execution kind of techniques across multiple devices or nodes. And the fourth and the one of the most important kind of dimension in this kind of an environment is the energy efficiency. So many IoT, because we are talking about IoT devices, so many IoT and edge devices operate under strict power constraints. So intelligent scheduling mechanisms, context-aware mechanisms, when to switch on, when to switch off, when to listen, when to forward kind of techniques has to be there. So such kind of intelligent scheduling and energy-aware computing mechanisms are needed for such kind of critical applications, and or if you are going for some long-term sustainable kind of applications. Likewise, as the project, actually I'm mentioning about the Periyar Basin project also, whenever we are putting some floating sensors on the Periyar Basin river, it also has to do such kind of monitoring for a longer period. We cannot often go there and recharge the batteries. It has to monitor the real-time parameters on a real-time basis, 365 days, 24/7. So we need to go for some kind of energy-aware scheduling kind of mechanisms for long-term sustainability. Most importantly, all these limitations, all these dimensions cannot be optimized independently, right? We cannot work on these dimensions. We cannot work on energy dimension alone. So that's why these dimensions are not independent. They are connected, they are dependent to each other, so they cannot be optimized independently. So decisions, why? Because decisions in one layer directly affect the others. So effective edge intelligence therefore relies on different joint optimization across different devices, edge nodes, the cloud, running a tightly coupled, tightly integrated intelligence system rather than a collection of different isolated compartments. So that's why nothing like, even though it is not about AI or different dimensions, AI, IoT, or any other kind of cloud computing systems cannot work on independent fashion. They are not isolated compartments. They are widely connected in order to have a sustainable kind of if we are going for building a sustainable kind of ecosystem. Okay, so these dimensions cannot be optimized independently. We need to go for a joint optimization, right? Can I take 10 more minutes, ma'am?
Sure, sir, sure.
Sure, okay. It's 8:53, that's fine. Okay. So so these are the main architectures for edge intelligence. So we have with the as I told you, there is a rapid growth happening this IoT and through different 6G frameworks, networks, etc. So centralized cloud processing is, we understood now that this processing is no longer sufficient. So edge intelligence addresses this by shifting all those computation, etc. So here you can see some examples of that. So these include, as I told, like AWS, but these are different frameworks. These are not just the company AWS, the generic AWS cloud platforms. There are, well-acclaimed, user-based, user-specific, or use case specific kind of frameworks, which is all, we can say that these are the mainstream AI frameworks, like include AWS IoT Greengrass, Microsoft Azure IoT Edge, Google Cloud IoT Edge, Open Horizon. So you can see, like, there is uh, one interesting project of Microsoft, which is again edge centric. You can Google it and find out what is known as Farm Beats, FARM, Farm Beats. Farm Beats is an intelligent AI-based, edge-centric, edge intelligence-based IoT solution for precision farming. And this is actually a combined effect of Microsoft along with University of uh, Utah in USA, along with University of Illinois. They are actually working on this kind of precision farming along with the UAVs and smart tractors, different kinds of machines and all, intelligent farming machines. They could have a predictive farming and all those kind of stuff. And they named the project known as a Farm Beats. And this Farm Beats actually connected, it is now available in 50, almost 40 or 50, like 40 states, I think, in America. And the majority of the farmers now, they are leveraging this kind of Farm Beats kind of intelligent platform. So similarly, AWS, Amazon Web Service also, they're having something called as AWS IoT Grass, Azure IoT Edge, Google Cloud IoT, then Intel Open Vivo, Vino, etc. So each of those frameworks adopts a different, they are having a different design philosophy, varying in the reliance on the cloud services, deployment complexity, so suitability, sustainability, suitability for different application scope or scenarios. So among these, I can say that AWS, that IoT Greengrass, which is a representative and widely adopted solution, because it actually, as I said about the Microsoft Farmbase, it extends the cloud capabilities to edge devices through a kind of a modular architecture that is being showcased over here in this diagram. So it extends the cloud capabilities to the different edge devices through this kind of architecture that could manage different runtime executions. They could and almost all the communications are secure communications and state synchronizations, and there are different isolated execution environments as well. So Greengrass, kind of a framework from AWS, offers or operates through different phases. Like there is an initialization phase, you can see there is an invocation phase, there is a computational shutdown phases, etc. All actually enables different manage messaging. They enables different device computations, on-device computations, efficient messagings, data caching, and machine learning kind of inferences. So performance evaluations nowadays, from that paper, I understood that performance evaluation shows that extremely low operational latency or in the order of microseconds are getting through this kind of AWS IoT Greengrass. Okay, so this is all about these mainstream architectures. Then moving on. So when we compare different computing, edge computing frameworks, this provide a comprehensive, a comparative overview of widely used edge computing frameworks that support edge intelligence across different dimensions, like whether it's a cloud dependent or not. How about the operational complexity? How about the deployment, that difficulty? What are the security capabilities and what are different application scenarios? So AWS IoT Grass, as we discussed in the previous slide, shows a high dependency on the AWS cloud itself, but in return, it offers a lot of strong security capabilities and broad applicability across different heterogeneous industries. So this operational, these kind of frameworks is highly operational, and the deployment complexity sometimes will be high because it is depending on different varieties of industries. So deployment complexity will be quite high. That reflects its functionality to be more cloud centric rather than edge centric. Then we have the Microsoft Azure IoT Edge following a similar philosophy and similar other kind of computing frameworks are available here, right? Then okay, different architectures. I'm just moving on. It's already 8:59, so I'm just skipping some of these kind of architectures, and so that I can give you some insights about the. You can just these are all generally available. Like what are the edge-centric architectures or frameworks? One from Intel, one from Google, one from Microsoft, and one from Amazon. I'm just moving on, and so here you can see like a different computational offloading and resource management in 6G. So so here you can see that we are moving into the first optimization domain of the EI framework, like how we can do the computational task offloading and resource management. So here also you can see that the features of 6G technology here, like there are working on terabits per second. So with terabits per second level, the bandwidth and the end-to-end latency is expected to be 0.1 millisecond. 0.1 milliseconds. So 6G enables a much more refined and flexible kind of execution model. So instead of moving towards building some static decision kind of communication frameworks, edge intelligence adopts a kind of dynamic, dynamic and hybrid kind of offloading approach. So each task here, or even each part of the task, is evaluated in real time based on the computational complexity, current networking conditions, and the capabilities of the device and edge servers. Okay. Then I'm just moving to the yes. So some of the challenges here are the technical challenges that which is again copied from the same paper, which arise mainly due to the mismatch between the advanced AI requirements and the limited capabilities of edge devices. So there are limited edge computing capacity of edge devices. So that is one of the important challenge. Limited computing capacity of edge devices. So we know that edge devices can be think of like a small sensor to some embedded system. Sensors could be a part of edge devices. Gateways are a part of edge devices, and embedded systems are also a part of edge devices. We know that all these categories of devices or systems have strict constraints in forms of memory, processing power, energy, etc. So running complex AI models directly on devices is often infeasible. That is one challenge. Then in order to address that, I told you like we need to go for some model compression, pruning and quantization, etc., to reduce the model size. And you need to work on the computational overhead while accepting there could be a trade-off. There could be a trade-off between accuracy and computational overhead. But if you want to run such kind of models at the edge side, you need to severely work on the model compression side, pruning and quantization side. And that are the methods to reduce the model size and computational overhead. So there should be a balance between a trade-off between the accuracy and computational overhead. Then there is a resource mismatch between different 6G networks and IoT devices. I told you that 6G networks is highly, it is extremely high. It offers extreme high bandwidth and ultra low latency. So many IoT devices cannot fully exploit these capabilities due to these hardware limitations. So that's why we talk about task offloading, distributed computing, and cloud edge collaborations. Then the third important limitation is difficulties in deploying complex AI models. I told you about you need to work on computationally incentive models, state-of-the-art models are majoritarily, they are all into computational incentive models. So you need to work on the lightweight models and federated learning, etc., to allow intelligence to be deployed, intelligence to be extended efficiently without requiring any kind of centralized data collection. Okay, and also one of the other thing we cannot avoid security and privacy, right? Security and privacy constraints cannot be avoided at any cost. So that becomes, so this is a major next challenge category concerning security and privacy, which becomes even more critical in large scale distributed EI systems. So data distribution security risks are there, right? Between data exchange between devices to devices. I told you about the UAV to UAV communication or UAV to the ground communication, etc. Edge nodes, networks. So making all them vulnerable to such kind of different kinds of inside and external side attacks, intrude or extrude attacks. So end-to-end encryption and secure communication protocols essential to ensure such kind of data integrity and confidentiality. Okay. So these are some of the challenges that as a researcher you need to look at. And when you look into the development trend of edge intelligence, now people are working on the multi-domain collaboration side. People are working on communication with AI, communication with different computing paradigms, applications, etc. Because I told you in the previous slides that without coordination across these domains, systems becomes standalone. They become fragmented. They are working in independent compartments, etc., and that makes the entire system inefficient. So we need to look forward to have related technologies, some interoperability and compatibility should be there. So for all practical applications, sustainable development initiatives, etc., we need to look forward to have the collaboration platforms. That's why FL has a huge role to play here. So these are some of the, and also now people like me, since I am into cybersecurity department of IIIT, we are working on different kinds of access control models as well, like role-based access control models and attribute-based access control models and all. So these are all related technologies where people are working on different blockchain assisted access control models. People like me, they are working on cloud-centric, edge-centric, attribute-based access controls and role-based access control models, where we can provide a level of security, because all the times when we are putting all these kind of security mechanisms, etc., in the edge side, we need to have a strong, balanced approach between security, safety, and practicality. So strong cryptography mechanisms will always give you strict security, but at the same time, it reduces practicality. So whenever we go for some practical, flexible kind of environments, we need to look forward to have a blockchain assisted. Blockchain-based systems are nowadays, that many practical applications, you can see blockchain-based systems are there. Therefore, secure and private, even for private, financial transaction, etc. For example, they're all blockchain assisted. So these are all some of the development trends happening in the edge side as well. People, if you're interested, you can work on secure access control models. One of the models is the attribute-based access control models or role-based access control models or blockchain-based trust mechanisms, the blockchain log mechanisms, etc. We are actually working on blockchain-assisted federated learning at the application layer of this, a multi-layer UAV security project. Okay. Then, okay, I think almost I have covered a majority of the things. So here you can see that these are the open research directions. You have to work on this cross-layer co-design of, because people are now, that's why in my project also, I'm not concentrating only on a single layer. So it's a multi-layer approach, a physical layer with data link and especially with application layer as well. So cross-layer co-design of AI, because it is not a single standalone system. We need to get, it is a foolproof kind of secure, multi-UV security we have to develop. So we cannot work on a single layer. We have to go for a cross-layer approach. So majority of the times, if for data link layer, we are working on CHA-20, Poly 150 kind of algorithms. The same capability can be extended towards the physical layer. Like, we have the physical medium dependent and the other layers, right? Physical layer as well, where these kind of, we could extend the capabilities of this CHA-20 150 polymer 150 algorithms for applications like edge based UAV to ground applications. So ground, we know that it's a physical layer approach. So we are actually, there is a spam kind of a communication. We have a Qn drone that is a prime drone, and this drone will be forwarding the collective data from all the drones to the ground station. There we are using Chacha 20, 150, Polymer 1, Poly 150 kind of algorithms for end-to-end encryptions. So these are some of the open research directions that you can look into. So always go for some papers, especially my humble suggestion for all of you, if you are new to this area, you can read papers on IEEE communication surveys and tutorials, or you can go and read IEEE communication magazines to have good understanding about the UAV assisted communications, UAV edge assisted communications, AI assisted edge, AI assisted. Then majority of the people, if you're looking for some funding from external funding and all, you need to have a very good use case. So nowadays, Government of India through this ANRF or any other kind of Anusandhan Research Foundation or MIT, they are not actually funding the conventional theoretical based projects. Those days are past. We need to have a minimum TRL level 3 or 4 at our end. So we have to convert all our theoretical ideas into product, and we do have the practical evidence with us. We should provide them a practical, a prototype kind of evidence. Okay, we have completed to this, and in order to move forward.
Participants, please mute your mic. Dear participants, sir, I accidentally muted you. Could you please unmute yourself and you can continue, please. Dr. Ragesh, am I audible? Hello? Hello? Dr. Ragesh?
Okay, so that's all about this presentation. So I have given, because with this 1.5 hours, I have given most of the kind of my ideas, my personal experiences related to edge computing and intelligence. So if you have any questions, you can ask me. You can go through my profile and reply to you also. If you want to collaborate with any kind of projects related to drones or IoT or similar kind of AI-based IoT projects and all, I'm happy to be associated with any one of you. So we aggressively work on different kinds of projects nowadays, especially on ANRF and many things. And like recently, we got many projects through ANRF and this ACN grant and through these kind of iHubs and all. So if you people are interested in some of these things and all, I'm happy to associate with you. So because there should be some kind of takeaway, there should be some kind of outcome through these kind of discussions. Otherwise, it becomes generally a monologue kind of. It has to engage in a dialogue, and only such kind of FDPs will become more more effective. Otherwise, it will be just another kind of a talk. So that's why I just mentioned about the different avenues where you can submit proposals based on such kind of edge intelligence, but always look for some kind of use cases. So with that, I'm concluding my talk for the time being. And if you have any questions, I'm happy to answer. Thank you.
Rakesh,
So
sir, I'm really happy that we are able to keep up our association starting from Saingist to till today.
yes, ma'am.
Now, but we'll take we'll continue our discussion offline, sir.
Okay,
You
sure.
also
I know that it's
coming
already
out of
9:15.
from your work, and I do not want to trouble you. I'm sorry. I
No,
know
no.
that.
Since see that I'm still in my office now, I
Okay.
want to travel to Kaladi in my
Okay.
bike actually.
I'm sorry, and thank you so
Okay.
much.
Okay then. Thank you so much. Yeah. Okay.
Thank you very much, sir, for the insightful session.
Thank you. Yeah. I think I'm trying to unmute myself, but some okay. Thank you very much. So no more questions, I think, from the audience side. Okay, thank you then. Shall I leave?
Yes, yes.
Okay, thank you.
Please take rest. Yes, thank you.
Dear participants, please note that the feedback link for today's sessions, both first and second sessions, have been shared in the WhatsApp group. Kindly fill it and kindly fill it before 10 o'clock. Also, uh, um, the FDP feedback, a document has been shared on the WhatsApp group. So you are requested to kindly download it and update the details for all the update the feedback and other details regarding all the sessions, all the 6 sessions for the 6 days. We will be sharing a Google form tomorrow, and you can upload your document in PDF format in that Google form. So kindly make sure by tomorrow evening you have completed the document. So thank you very much. Have a good night. We'll meet tomorrow, which will be the last day of the FDP. Thank you very much.
So just a gentle reminder, tomorrow the session starts at 2 p.m.
Yes, participants, kindly note that this first session tomorrow will be from 2 p.m. to 3:30 p.m. And the second session will be from 3:30 to 5. Thank you very much. Good night.